So our opening question is use the pie chart to answer the following questions. So here we have our pie chart again, looking at how far cancer has spread at the time of diagnosis for lung cancer patients. So our first question is, when are the majority of lung cancer cases diagnosed? So when we're looking at our pie chart, this doesn't tell us at what time in the development of the lung cancer, so time-wise, but what it does tell us is that by the time most patients are diagnosed, the cancer has already spread. Okay. So it's not at the very beginning of when their cancer is, but usually a little bit later in the development of cancer. What percent are found locally? So this tells us that 15% have cancer in their local area from where the original lung tumor is. Our next question is, how might we improve outcomes for lung cancer? Again, what this tells us is that by the time a patient is diagnosed, that with lung cancer, they probably have cancer somewhere else in their body, and so as a cancer doctor or healthcare provider, you would look for cancer in other places, so maybe such as a brain tumor or a bone tumor, with further testing like an MRI or a CAT scan, and then that patient will probably need more aggressive therapy to help improve their survival outcomes. Scientists use different types of studies in different situations. So some of our experiments are hypothesis driven. So we have controlled experiments that allow scientists to test a hypothesis. So if we look here, our scenario, our researchers hypothesized that a new intensive therapy would benefit patients with type 1 diabetes. Type 1 diabetes is where an individual's body no longer makes insulin, and so a person with this disease has to inject themselves with insulin every day. And type 1 diabetes can lead to things like nerve damage and things like eye damage. Over time. And so what we're looking at here is we have two groups of patients. One group we gave regular therapy, which would be regular insulin, while the other group we gave a more intensive therapy. And so then we look at their outcomes over time. And so what we can see here in this case is people in the control group had higher eye damage and higher nerve damage. So what we can take away from this is that that the intensive therapy benefits our type 1 diabetes. So in this case, we can see that the data supports the hypothesis of our hypothesis-driven experiment. Some studies are observational. This allows scientists to examine objects without manipulating them. Again, we frequently do this with ecology or a field test where we go out and we watch and we record information. So for instance, we might do this with the squirrel experiment that I talked about before. We also do this with humans, and this is something that is going on intensively right now in the area of public health, where we can't take humans and necessarily stop giving them a treatment or just give them any treatment, which could potentially be harmful to them. So instead, what we do is we take humans and we can look at things like their lifestyle. So what are they eating? How much exercise do they get? What things are in their environment? Do they live in an area where there's lots of exhaust, for instance, in an area that might have a lot of cars or factories, or do they live in an area where there's a lower density population, so maybe fewer people in contact with one another, and then we can pull that information and come up with a conclusion. Epidemiologists measure links between lifestyle and health over a long period of time. Again, this is where we see those observational studies done with humans. So for instance, if I'm looking at going back to environmental hazards. So, for instance, I might hypothesize that living near a particular factory is going to have bad health outcomes for my patient. Maybe I can say individuals who live near this factory are going to have higher rates of lung cancer. And so it would be unethical for me to take healthy subjects and expose them intentionally to the chemicals of this factory to see if they get cancer or not. And so that's one of the reasons that a lot of these studies are observational, because intentionally exposing humans to certain conditions would be unethical or unsustainable, would not be able to do from logistic point of view. So an observational study that I could do is I could look at individuals who live near the factory, and I could look at individuals who didn't live near the factory, maybe on the other side of town, and I could count how many of them develop lung cancer over a 10 or 20 or 30-year period, and then measure those numbers and see if more people who live near the factory have lung cancer versus people who live on the other side of town after 20 years. And then that data would support my hypothesis. So here in my study, I'm looking at researchers hypothesize that there would be health differences among those using injections and those using pumps. So again, we're going back to our type 1 diabetes. So type 1 diabetes, the patient gets insulin, it's injected in their body. It can be injected with a syringe, which is what an injection is, or it can be injected with a pump. That's where sort of a continuous flow of the insulin into the body with a tube. And so what our researchers are suggesting is that that there would be some type of difference in the method that the patients get the insulin. And so we can look observationally over time at patients who are doing injections versus pump, and we can look at their health outcomes. So in this case, heart disease is also another problem that's caused by type 1 diabetes, as well as early death. And so we can look at and see after a certain period of time how many patients had each of these occurrences in my two different groups. So again, I can quickly look at my data here, and I can see with my bar graph that yes, there is a difference among individuals who use injections versus pumps. So individuals who use pumps are less likely to get heart disease and less likely to have an early death. Again, my data supports my hypothesis. Clinical trials are controlled experiments that use humans. So every drug that's out on the market had to go through rigorous testing to make sure that it was both safe for humans as well as actually worked for its purpose. And to do that, we did a number of clinical trials. So there's different phases of clinical trials. When we do a clinical trial, the first thing that we look at is to see whether or not something is safe for humans, and then the next phase or step in the clinical trial is to look at whether it actually works for its intended purpose. So when we do this, subjects are randomly assigned to an experimental or a control group. The control group receives a placebo or a treatment that doesn't contain a substance being studied. So in this case, I'm looking at a control group who's getting normal insulin therapy and a placebo injected versus my experimental group who's getting normal insulin therapy and a drug injected. So in this case, I'm looking at my type 1 diabetes, and I'm suggesting that in addition to the insulin, if I give a second drug to my patients, maybe it will improve the outcomes in these patients. And so again, I can look at my independent variable is what I'm changing between my two groups, and then my dependent variable is what I'm going to measure and see whether or not that supports that. We do this in many different medications, so something that might make more sense is an energy drink, so or a high blood pressure medication. So lots of Americans have high blood pressure, which is where the blood pressure is elevated, and it can cause things like strokes and heart attacks, and many people don't even know that they have high blood pressure. And so we treat high blood pressure with diet, and we also treat it with medication. And so let's say I'm a drug company and I've come up with this new wonder drug for treating high blood pressure, and so my hypothesis is that my new drug treats high blood pressure better than the drugs already on the market. So in this case, I'm going to have two different groups. I'm going to have my control group who's going to get the drug that's already on the market. Or I might give them a sugar pill, so something that doesn't have any medicine in it at all, so a placebo. And then I'm going to give my other group my new wonder drug that I've made. And then I'd say I'm going to give the drug for 3 months, and I'm going to have my patients take their blood pressure every day or once a week for 3 months, and then I'm going to measure their blood pressure. And so if my group with my new drug has lower blood pressures than my control group, that proves that my new drug works better. And that's the idea of a clinical trial. So our opening question is, we use a graph to fill in the correct answer. So here we have an epidemiological study that follows 18,000 people for 7 years. The results suggest that those using insulin pumps were about blank as likely to experience heart disease and death. So if we look here, we can see that those with injections were 10 times have 10 problems per year, while those with the pump only had about 6 problems per year. So we can see that they almost have half the number of problems per year. So they are so those with the insulin pumps were about 50% as likely to experience heart disease and death. Critical thinking is required when evaluating scientific claims. So again, science is not just a whole bunch of facts that you're going to memorize and then rewrite like you would vocabulary words. There's something that you are going to use, and you have to think about what type of question you need to ask. You have to think about what type of hypothesis, and then you have to critically think about the data that you got. So science has hallmarks and limitations. Many of our limitations are related to some of our technology. We can't measure everything, or we can't measure everything as accurately as we would like. Critical thinking is an unbiased analysis and evaluation of information in order to form a judgment. So that means we don't want to have bias. So for instance, if I go back to my cookie experiment and I'm looking at taste of cookies, and so in my mind, if I think cake flour will make better tasting cookies than all-purpose flour, then when I go to taste my cookies, if I already have this idea in my head, then I'm more likely to think that the cake flour cookies will taste better because I have this thought in my head. That's what a bias is. And so we want to get rid of those biases when we're doing our evaluation. Critical thinking can help you recognize pseudoscience. So pseudoscience, so the prefix pseudo sort of means pretend. So it's pretending to be science. So again, the parts of the words we use are important. And so pseudoscience is something that is not critically experimented on, does not have a lot of data to prove to support an idea or refute or an idea. So when we're comparing features of science versus pseudosciences, some of the ways that we can tell the difference between the two is that in science adheres to an established and well-organized scientific method. That means we go through those steps. We make an observation, we ask a question, we come up with a hypothesis, which is an educated guess. It's not just something we pull from thin air. It's based on other experiments or other background knowledge that we've been able to attain. It's testable. We're going to get results, and then we can use those results to either support or not support our hypothesis. Features of pseudoscience do not adhere to a generally accepted process of science. So we skip one or more of those steps. features of science is that it's repeatable. That means I can do an experiment and I can do it again and again and again, and I will get the same or similar results. So in this case, if I look at my cookies and I'm comparing my cake flour to my all-purpose flour, in this case, I could, if my cake flour makes taller cookies, or better tasting cookies, that means that every time I make a batch of cookies with cake flour, they will always be higher. They will always taste better than every single batch after batch after batch of all-purpose flour cookies that I make. With pseudoscience, results cannot be duplicated by others. That means another group of researchers, or even the same group of researchers, cannot do the same experiment and get the exact same results more than once or more than twice. Or the results rely on a single person or somebody's opinion. Testable claims that can be disproven. So our experiment is capable of giving us data that does not support our hypothesis. Okay, we can disprove our hypothesis. Whereas with pseudoscience, it's unprovable or untestable claims. So there wasn't an experiment done. We're always going to get the same, we're going to get results that show what we want. We rely on assumptions or beliefs that are not testable. Features of science is that it's open to outside review. That means I can, as a scientist, I can do an experiment and write all these steps and get my data and make my graphs, and I can give it to another scientist who can look at my experiment and say, yes, this was a well-controlled experiment. This data makes sense. Whereas with pseudoscience, I get rejection of there's rejection of external review or refusal to accept contradictory evidence. So that means that another scientist is not going to look at the experiment or the data and say, okay, this was a good, well-controlled experiment. Or there might be a whole bunch of other similar experiments, but they have results that do not support that hypothesis or that idea. And so features of science is that multiple lines of evidence. So we have different experiments with different types of technology, different types of measurements supporting that idea. Whereas with pseudoscience, we have an over-reliance on a small amount of data. Underlying causes are not investigated. So for instance, you'll notice that one of the studies that I talked about in a previous example looked at 14,000 individuals. That is a good controlled study that has a large a number of test subjects. So the more test subjects we have, the better the data is. Whereas if I only looked at 5 people or 10 people, this is a very, very small group of people where I'm getting a small amount of data. And so this may not really support the idea that I'm trying to test, because those 5 people or those 10 people might be outliers and not similar to the general population, for instance. Some examples of pseudoscience include things like fortune telling. Pseudoscientists often use scientific seeming but useless gadgetry. So, for instance, technology that hasn't been proven to get accurate measurements or the measurements that it's claiming it can get. Predicting personality traits based on skull measurements or claims of ESP. Scientific studies can be performed well or poorly. Critical thinking is important to decide that an experiment we did is good. And so one of the first things we want to look at is sample size. This is the idea of how many subjects we're going to have. Something with a larger number is going to be a better experiment. So if I've got 100 people, 1,000 people, or 10,000 people, it's going to be a better experiment than one with 5 or 10 subjects. I'm going to have a good control group. That means I'm going to have a group that I can compare to. So if I go back to my blood pressure experiment that I talked about for an example, making sure I have a control group that's already getting the current treatment or no treatment at all so that I can compare my new drug to it. and that I have reproducibility. That means the experiment can be done again and again and again. I can redo the experiment and get similar results. Another scientist can do the exact same experiment and get similar results. Um, Different sources of information have different degrees of reliability. We have things that we call primary sources. This is the original material presented for the first time by the person who actually did the experiment. So the scientist who actually did the experiment and made the graphs and came to the conclusions. We frequently see these in what we call scientific journals. They're sort of like technical science magazines. Good primary sources are ones that are peer reviewed. That means other scientists looked at the experiment and looked at the data and said, yes, this is a good experiment. It has good control groups, it has the right number of subjects, it was reproducible. Secondary sources are descriptions or reviews of the primary sources. So for instance, a primary source would publish my if I'm a drug company who's made this new blood pressure drug, a primary source would be publishing my results about current therapy versus my new super drug in a peer-reviewed journal. Secondary information would be like the New York Times or the Washington Post or some other news outlet going to the primary one and then writing an article. It says drug company makes new wonder high blood pressure drug, but doesn't give all of the details and the graphs. And then there's Wikipedia. Wikipedia is a common first source, but allows anyone to create or edit articles, so it's not as reliable. It's not that Wikipedia is a bad thing. It's actually a really good starting point to give you information about topics. However, anyone can edit it, so you have to take what it says with a grain of salt. The best thing to do is start with Wikipedia, and then if you go down to the bottom of Wikipedia, it will give the references for that information, and actually going to those references and reading that information is more reliable. Again, we want to look for things that are peer-reviewed. Peer-reviewed means that other qualified scientists who are anonymous, they're experts, have looked at an experiment and said, yes, this is a good experiment. It has the right number of subjects, the graphs look good, it has a good control, and the results were reproducible. We frequently refer to this as the gold standard. Peer-reviewed journals are the best source of information. Recognizing reliable sources of information is an important skill, not only if you're going into science or healthcare, but just even in general life. You might be making decisions about what products you're going to buy for as a consumer for yourself or your family. And so being able to really decide that a source is reliable about the information for that product is important. You are maybe a individual who's able to vote or voting soon, and so you need to be able to read reliable sources related to the topics that your legislators will vote for. So for instance, if you agree with a certain idea, being able to read information about that idea and understand that idea, and then to make your decision on whether you're going to vote for or against somebody who agrees with or disagrees with that particular idea. So things that we want to look at when deciding whether a source is reliable or not is the information current? Is it something that was published this month, this year, in the last 5 years, or it's something from 1950? Is the source primary and not secondary? So how many times was it repeated before you got that information? Is the author identifiable and well qualified? So is it somebody who is, for instance, a researcher at a university who's got a degree in that field? Does the author lack potential conflicts of interest? So if I, for instance, am a scientist at the drug company who made the new high blood pressure drug, I have a conflict of interest in that experiment because I want my drug to work better so that I can put it on the market and sell it. So in that case, I would have a conflict of interest. And so authors who have conflicts of interest may not be as unbiased when they're analyzing the data. So you want to look for an author who does not have conflicts of interest when they've published something. So that means they don't work for that company or they're not being paid by that company. Are the references cited? So where did they get their information from to come up with their idea, or how did they do their experiment? Are any experiments described in enough detail so that they can be reproduced? That means, can another person read their paper, read the information, and be able to do the experiment themselves? Was the information peer reviewed? Did other experts look at it? Is the information unbiased? Is the intent of the source known and valid?